Assalamu alaikum, everyone. So today we are going to have lecture 15, EE341, microelectronics. So what we are going to do today, we are going to mainly focus on some of the examples related to the frequency response, which we were continuing from last 3 lectures. So we have initially seen what about the frequency response, talking about the Bode plot, how we can do that one, and then we move forward, and we have seen the how to find at a specific node, find the impedance and the capacitance related to that, and then if that capacitance is in between two nodes, how we can find the capacitance from that node to the ground using the Miller theorem. Then we have applied that complete analysis on common source amplifier, common source with degeneration, and common gate amplifier. Now, today will start with a source follower, and we'll apply on a source follower, and then we'll move towards cascode and might be on the differential pair, and we'll see some of the examples from your book. So moving forward, the first thing we want to have as your frequency response on a source follower. Frequency response on SF. So FS is a source follower, right? So let me draw a simple source follower, and then we can proceed towards the calculation of your source follower. You can take from your VDD, you have here some junction where you are applying your input ultimately. So first I will just draw the overall circuit, and then we will see how we can solve this circuit. And just let's draw some resistance RS here, something which we applying an input, and also we are applying some RS. So this is our output, V out, and along with that we are having a load impedance. Let's say call it as an RL. I just want to stick to the same terminologies that your book is using. So here what we are having the circuit, and now we want to, this is the common source follower which we have seen. So here we have a series resistance. We just put, because the source, we have some series resistance, and then we also have some load resistance. So our main intuition is that we want to find the capacitance. So first of all, we need to draw the capacitance, rather the high frequency capacitance. So we will draw the high frequency capacitance. Okay, high frequency capacitance. अब high frequency capacitance कौन सी होती हैं? Those that transistor capacitance. So CGS, CGD, CGB, and CGS. So in this case, what are the capacitance which are going to play? So first and the most important will be here C gate and source. So CGS. So one capacitance will come in the form of a CGS. Another capacitance will be at this one, let me draw, and then we'll see which one will be CGD. So we have one capacitance CGS, one capacitance named as CGD. Then we have drain to body capacitance. So somehow I will draw it and then we'll remove which are not used, CDB. If you see the CDB and the CDB is basically the VDD is a virtual ground. So that will be equivalent to 0. So there is no capacitance here, but still let's keep it as it is. But in this question in the source follower, we have explicitly CSB, source to body or the source to bulk is present, which was not present in the case of a common source amplifier, which was not present in the case of a common gate amplifier also whenever we were applying the input at that point. But whenever we are applying and we are seeing amplifier where the source and the bulk are not grounded together, then we are going to observe source to body capacitance. Just one correction, common gate will have the source to bulk capacitance. There we will have a different scenario, but the source to bulk will be present since we are not grounding, or we are not shorting the source with the bulk, rather the source is an input point in the case of a common ground. But in this configuration, we have a CSB, CDB will be equivalent to 0 because VDD will be AC ground, CGS and CGT. So we know what we have to do all the time. So we have to identify the nodes. We have to apply some configuration so that we can figure it out, the stuff. So let me just simplify the circuit so we can have which capacitance are basically ultimately mattering for us. So this is going to be AC ground, VDD. So we are not going to be concerned with the CDB. Here we have RS, which is an input resistance, which is going to be seen at this node. So we have one capacitance here, RL. We have CGS. We have CSB, and here the source to gate one will also come here because the drain is AC ground. So we can write CGD here. Okay, so CGD will be to the ground here, that will come an input capacitance, and CSB will be here. If we further simplify this, we again see there is this is input and this one point was an output. So we have some same configuration, which is some sort of Miller, that we have an amplifier, okay, and we have a capacitance, in this case CGS, in the middle. So we need to do something with that one. And we know whenever we have such situation, we can divide this into two capacitances, CGS, CG1, for example, on the input side, and CG2 on the output side, with the formula which Miller basically help us to evaluate. So if you want to directly apply that formula, we can come to the notion. Let me just draw it here. So the circuit will look like, simplified circuit will look like, we have an input here, we have some resistance RS, and input side is this point, and just keeping some gap here so that we can mention all the capacitance. So CGD will be given to us. CGS will be now coming in the form of a CGS times something, and that times something is what is going to be important point. CGS will be 1 minus AV. So here we have to be a little bit careful that the gain of source follower is not inverting, rather it's a non-inverting gain. So whenever we have a non-inverting gain, the capacitance is going to be this form, 1 minus AV. Previously, whenever we are seeing common source, we do the CGD, but at that time it was 1 plus AV because the gain was inverting. Here the gain is non-inverting, so we'll write CGS into 1 minus AV. So the capacitance value is ultimately going to be reduced. We are going to see how much in a couple of a moment. So this is going to be like this. So this is AC ground again for us. And this point will have again RL and CSB. CSB will as it is come. And then along with that, we have another capacitance, which is CGS, same thing, 1 minus 1 over AV. Same thing again, exactly. AV is going to be minus now, AV over expression next to AV. So ultimately the capacitance will go down as compared to the CGS. So now we have this computation. I will just plug in the numbers of AV to evaluate in a while, but just make sure to you grasp this concept, the difference from common source to source follower. Again, the Miller theorem is applied, but in this time when the Miller theorem is applied, ultimately your capacitance or the input capacitance is reduced based on the proportion which is coming. That is 1 minus AV. Previously, it was 1 plus AV. Why? Because of the non-inverting nature of source follower. Okay? So it's AV here. In common source, it was invert. In common gate, there was no capacitance coming between two nodes, so we were not even applying Miller theorem. Right. So moving forward, if we want to do the gain of this configuration common source, source follow, right? If I want to do the gain of this thing, the DC gain, so let me just draw a simple again circuit for you. So if you want to have, so here with the gain is from this point to this point. Here there's an RL and this is an output. So we are applying input and we are applying an output here. So and if this is M1, so the gain AV, which is again a positive value, if you all recall, was somehow equivalent to RL in parallel with, if this is not, L lambda is not equal to 0, this is equal to RO1 divided by 1 over GM, which is the transconductance 1 over impedance plus again RL in parallel with RO1. Right. So for simplicity, what I will do, I will just plug RO1 again just to compute something, and then later on we can bring it. RO1 is equal to infinity. Okay. So lambda is equal to 0. Just if in this expression we plug in, we will come out. I will just go to the next page, and then if something is needed, we can draw, we can bring it back. Let me write it now. So AV, if we put RO1 is equal to infinity, will be equal to RL divided by 1 over GM plus RL. Okay, that is if RO1 is infinity. Now let's plug in that formula which we just have. That new CG1, which we, let's say C1, let's call it. We didn't give a name there, but that I may call 1 minus AV, it's not AL, AV was equal to CGS. So let's put it 1 minus RL divided by 1 over GM1 plus RL times CGS, which will become 1 over GM1 plus RL minus RL divided by 1 over GM1 plus RL times CGS. RL will cancel from RL, so we'll be left with something which is going to be 1 over GM1 divided by, let's do that math. So it's going to be 1 plus GM1 RL divided by GM1. So this is going to be cancelled out. So our C1 will be equal to CGS divided by 1 plus GM1 RL. Or if GM1 RL is bigger, C1 will be almost equal to CGS divided by GM1 RL. So we can see the important point here, the capacitance, the input capacitance, because of the non-inverting nature which is coming here, C1 value is reduced as compared to CGS, which is not the case in the case of a common source amplifier. So that's all of you need to make sure you clear this thing. Okay, CGS. So here this is AV, it's not negative anymore, AV. So the C1 basically ultimately becomes like this. And something, if we want to do the same thing on the opposite side, C2, we can write also, just plug it and write the expression. Again, the RL will be cancelled out and we will have some relation which we can write at this node. So in this way, you can configure according to your requirement. Okay, so that's very much important thing. We have the input capacitance, we have the output capacitance. So the capacitance is okay, we can evaluate the capacitance. But what about another important thing? What was the impedance? So what is the impedance at the nodes? That's a little bit tricky now when we are going to evaluate the the impedance. That's not going to be that much straightforward because the impedance also will start becoming frequency dependent as opposed to the previous scenarios. Okay, so how it will be frequency dependent? So it will be if we just draw that thing circuit. Here is RS. So in this node, when we will find the node omega P1, omega P1 will be equal to, okay, 1 over RS times whatever the capacitance we find, C1 times the CGD capacitance. ठीक है, so हम लोगों ने ये capacitance देख ली, we can figure out. And omega P2 क्या हो जाएगा? Omega P2 will be equal to omega P2 will be equivalent to 1 over some impedance that I don't know what is that impedance. We just need to figure it out. R Thevenin, let me write it, times we know the two capacitance coming C2 into another capacitance which is coming as CSB. So we have two capacitance here. So it's going to be R something. Capacitance, we figure it out, how we can figure it out, the capacitance, but and RS is also known. But what about this R Thevenin or something? What value it will carry? So we can do a small signal model because it will not be definitely RL only. There will be something more than that. So let's see what's going to be inside that value. Let me draw that thing. So इस node पे हमने impedance find करना. So we can do a small signal model again to figure it out. M1, let's see. मैं इसी का draw कर रहा हूँ. M1, GM1. Just 1 second. Yeah. So GM1 and times GM1 times VGS, for example. This point is VGS. Just wait for a moment. Let me make things are aligned, and then I will bring some notions which are very much important also in clarifying these things. Okay. So initially, if you want, we can assume RO is present or no. So we can take RO as infinity. Okay. RO come infinity le lete, meaning lambda is equal to 0, just to make our life a bit easy because we want to conclude something. Even if I do, it will not matter much. Just an factor will come. So this is AC ground. So this is the drain point, which is AC ground. So we have here the junction, which is RL. Okay. So we have an RL here. And what we want to find the impedance at this point. So if we want to find an impedance at this point, we need to find a DC source, short this point, DC source Vx, and want to find current Ix. So if we want to do this impedance will be taken out because whatever is going to be, that will be in the parallel with the RL, so we can take this thing out easily. So that's going to be. But one important aspect in this moment is that here, this impedance output becomes frequency dependent. And because of this frequency dependence, we need to bring this CGS also in the CGS. So let's draw this CGS here and see the impact of this CGS. So this was the source, this is the drain. So here we have some point between this one, CGS. So here, this is the gate point, and the gate point is connected to the RS. When we're finding the impedance, all the independent source will be grounded, so input will be grounded. So now we have this configuration. Let me redraw it a little bit more. It's not clear in a better way. So we have here GM1, VGS, we have here a ground terminal, and here we are applying a DC source to a test to find the impedance at this node, which we called R out or Z out, since the capacitance is also involved. And this is a source terminal. So source terminal has a CGS. And then we have a gate here, RS, and that's the ground. Okay. So now if we want to write the current, we can simply write the current in a form that Ix will be equal to minus GM1 VGS, okay, plus, so this Vx node was the Vx divided by Rs plus 1 over SCGS, okay. And also we know that since input is 0, we in 0, which was equal to VGS plus Vx, okay. So हम ये लिख सकते हैं. And if we want to write this thing, this means that VGS is equal to minus Vx. So we can write Ix is equal to GM1. I make it positive. I replace with the Vx plus Vx divided by Rs plus 1 over SCGS. I will bring it to the next page and then we'll do the corresponding math there because there's something important we want to draw in the next one. So this, let me recall this one, I don't miss it. So we come to some conclusion that Ix is equal to Vx if we want to take it common. I will go back to see the expression a bit. So it's Gm plus some expression. Yeah. It's Gm plus 1 over Rs plus 1 over SCGS. ठीक है, ये हमारे पास expression. If we just plug it and try to sort it out, the Vx will be equal to Gm Rs Gm plus 1 over or Gm divided by SCGS plus 1 divided by, so we just took all the things and we are left with Rs plus 1 over SCGS. You can do another way too, but I just want to make sure that what we are doing makes sense. So if we want to write in this form, it's going to be GM CGS RS plus GM bringing this, but over plus S CGS. Okay, but as we increase the frequency, as we go higher, the impedance is not more 1 over GM, rather it becomes RS. And that's something which we need to be careful. Okay? So the impedance is frequency is equal to 1 over GM. So if, for example, we assume RS value is pretty much bigger than 1 over GM, just for mimicking it doesn't matter. So if RS is bigger than GM at lower frequency, if this omega, my impedance is 1 over GM, and at a higher frequency, it will become RS. So this is RS, this is 1 over GM. If GM is 1 over GM is bigger than RS, then what's going to happen? Vice versa. So we are going to put GM and then it will go like this with the help of increasing frequency. So this will be 1 over GM and this will be equal to RS. How it came out, we just plug it S is equal to 0 to find the extreme. If you put plug S is equal to 0 in above Vx over Ix expression, it will be equivalent to 1 over GM. If you plug S is equal to 0, meaning DC frequency or 0 frequency or DC. Or also if you put Vx over Ix, S is equal to infinity, it will become approximately equal to Rs. So if S is approaches to infinity, meaning at higher frequency. So you can just plug it, take the S common and try to cut it out and you will observe the behavior yourself. That, okay, this S will be cancelled out, this will become 0. So at lower frequency, Vx over Ix will be 1 over GM. At higher frequency, GM over S, so that will become 0. And we will be only left with this RS terminology. Okay? So if we do this thing, we can figure it out. Right? We come to the conclusion that we follow this behavior. And what about this behavior which is being plotted here, especially the one on this side? At a lower frequency, we have a lower impedance. At a higher frequency, the impedance is increasing. Can anyone guess a little bit? Think about some component, a passive component, which shows this behavior. We saw the capacitor, how the capacitor behave. The capacitor, resistor. So capacitor, as you increase the frequency, the capacitors, if I see XC, goes down. At a lower frequency, we have a higher capacitance. At a higher frequency, we have a lower capacitance. We all know this thing. Resistor, ideally independent of frequency. Whatever is impedance at 1 hertz will be the same impedance at 1 gigahertz. Good. What about the inductor? Inductor is XL, 2 pi FL. As you increase the frequency, the impedance increases, resistance increasing. So it's the same phenomena which is being here. At a lower frequency, it's 1 over GM. At a higher frequency, it's RS. And we assume that RS is bigger than 1 over GM. So we mimic an active inductor using a MOS, a source follower. And that's something which we normally use. Because otherwise, to integrate inductor on chip is daunting, it's challenging to have higher values. So one way to integrate an inductor on chip is to use a source follower and get the benefit from this behavior. So that's also very much important phenomena which you need to keep. So now let me do one example related to the source follower, and then we'll move forward to another example. So this is example 11.24. In example 11.24, what basically you're having is some, again, a source follower sort of stuff. Let me just check. Yes. Yep. So let me just do this thing. So we have a source follower. No, what's the sorry, I missed this. Is not example 11.4. 24, example 23. I just missed it. That example is of 2-stage. That also we can do, but let's first start with the source follower. So if we finish the topic of a source follower, so we have again a source follower V in, and we have here current source, basically VB, okay, which we call M2. So, and we want to find the input capacitance of the circuit. So we are told to find the input capacitance, meaning we need to find C in. Okay, so we all know the scene will be combination of what we need to draw those circuit. But before drawing the circuit, let's have a bit quick configuration of this overall circuit. So I will just let me draw rather here. So now we know there will be some capacitance. So those capacitance will be what we will have. We will have CGS, because the signal capacitance are going to matter. So we'll only draw this capacitance at this moment. But this point is going to be virtual ground, AC ground. So we are not going to concerned about this point. This point is AC ground. We are not concerned about this point. So this capacitance, and on the input side, another capacitance is going to be CGD. Okay, so ये दो capacitance input side पे आ जाएंगी. But in order to bring the C in, we need to write CGD plus CGS times 1 minus AV. So AV हमें पहले find करना होगा इस, ठीक है? तो AV इसका किस तरह find करेंगे? If we want to write the gain of this one, what will be the gain of this amplifier? So impedance seen at this point is RO2, and this is your V out. Okay. So let me draw the small signal model, and we can find AV of the circuit. We might have done the similar in the source follower, but just as a revision, I'm only doing the gain of this configuration. So let me draw here, and then we can. So here I can just easily draw. Okay, now we have instead of a load, I have some impedance which is known as RO2. ठीक है, ये मेरे पास V in था and this is my V out. हमें पता चल गया कि ये हमारे पास V in है, ये M1 है. So इसका अगर मैं small signal model draw करूँ, it will be GM1 VGS. ठीक है, so this point to this point will be VGS, and that's interesting thing which we just want to see. And then we have also something RO1. This point is grounded, AC ground hai. And then we have between this point and again this point, another thing RO2, and here that we have V out. Okay, so if we want to write the expression, we can have this one is V in, and also we know now V out is equal to or V in rather is equal, just 1 second, let me write it. Yeah, so we can easily write that V in, yeah, V in is equal to V out plus VGS1. This is VGS1, okay? And VGS1 is equal to V in minus V out. Fine. So what's our output? Let's make it 1. And our output, if we just again further simplify this circuit, is equal to current is flowing through this, some current GM VGS is flowing, AC ground, flowing through some node V out. And what is this node has? Has two resistance, RO1 in parallel with RO2. Since this point is AC ground and they both are replica, so it's going to be RO1 in parallel with RO2. So V out will be equal to GM1 VGS1 times RO1 in parallel with RO2. Okay, and we can just plug the 1 into this equation. We will be left with V out will be equal to GM1 V in minus V out multiplied by RO1 in parallel with RO2. This one, let me rub this thing. Yes, and that will bring us AV, the gain equivalent to RO1 in parallel with RO2, which we all are familiar that, okay, 1 over GM1, not like something new, जो हम लोगों ने start में भी किया था, but just I want to do okay, how it's coming if you just want to refresh it. 1 over GM1 plus RO1 in parallel with RO2. Okay, so this is the gain. So now we'll plug this gain formula into this expression of 1 over AV, and we can figure it out the same thing हम लोगों ने पहले किया हुआ. So if we just plug it, or relation will be something, अगर मैं C in लिख दूं exact complete, it will be CGD 1 plus, let me just write in a, just don't miss something, CDS1. So it will be CGD1 plus 1 minus AV. If we just do this thing, it will be 1 plus GM1 times RO1 in parallel with RO2. So again, we saw the capacitance ultimately reduced. And if we just see this value is not worth as compared to CGD, if needed based on the values, we can also do this assumption. But it totally depends upon the value of CGS and the value of this gain. Okay, so GMRO kitna hai, we can do this thing. But in reality, this is our input capacitance. And that input capacitance will be multiplied by RS, and we can have a pole information available to us. Okay? So that's all about source follower, which we did. Your book is talking a lot about BJT. Again, we are not covering anything about the BJT since it's not that much we use nowadays, but the same analysis can be applied. And second thing, the book is talking more about the direct analysis, meaning drawing the complete capacitive model with a hybrid pi model, meaning small signal model with those capacitance, and then trying to solve out and reaching to the same conclusion. You don't have to do that thing. You will not be asked. You're only going to be asked that for if you want to do the frequency analysis, you need to do the small signal analysis for DC gain. And once you find the DC gain, you need to identify the nodes for the specific capacitance. If they are Miller, you have to identify or apply Miller theorem to identify the individual nodes, and then you need to find out the pole information from those, and then you have to find the overall transfer function by applying the equation and draw the Bode plot as required. Okay? So that's for that thing, and then just we will apply the same frequency response on a cascade stage. हम लोगों ने cascade जिस तरह किया था, so we can also apply the frequency response on the cascade. ठीक है, so for frequency response, so cascade, let me draw a cascade circuit for you, and then we can see what's different thing is going to happen. Cascade में यही होता है, you have so now you can see all the same things are linked with each other. So if you just have some fundamentals, you can easily tap a lot things. Okay, so here we have RS, here we have M1, and here we have M2. So interestingly, frequency response, अगर आप देखते थे, we want to talk about V out. V out was something here, and we can easily find the gain of the amplifier. But यहाँ we have Miller capacitance. To draw कि Miller capacitance कौन सी है? So here as a Miller. So we need to draw all of them. I will draw in a like an example I will do in a couple of a moment, but let's do the CGD1. इस CGD1 को हम किस तरह sort out करेंगे? That first we need to see. So CGD1 को हम लोग क्या करेंगे? We need to divide into capacitance. Again, we have first stage M1 का है. We have CGD1 here. ठीक है? तो CGD1. So we want to divide into two capacitance. यहाँ से gain negative है. So those two capacitance will be something like this. ठीक हो गया? C1 will be 1 because the gain is sorting. CGD1 and C2 will be equal to 1 kV times CGD1. ठीक है? So the important thing we need gain, overall gain नहीं, gain of first stage, let's say, or this one from this point, अगर इसको x कह दें, इसको y कह दें, this is x and this y. So we will find gain of AVXY, which is equal to AV1 जिसको gain can ignore RO. RO will be equal to infinity. If RO is equal to infinity, normal gain of a common source is what? GM RL. What is the RL from up? 1 over GM2 we are seeing from the source. So it's 1 over GM2. So the gain is equal to times 1 over GM2. So ये हो जाएगा minus GM1 divided by GM2. That is the gain for you. And you will just plug it. Yeah, sorry here, since I already considered minus, so I can take liberty and I can write the plus sign. So you just plug it in this number, can find the capacitance, and already clear to us. जो यहाँ capacitance होगी, that's clear. We will do one overall combined example to sort the things out. ठीक है? So let me just do a combined example. We did this Miller one, so I will do a combined example to clarify this point now. Let me try to do a bit modified. So first, let me draw the circuit, and उसके ऊपर I will embed the all capacitances. ठीक है? Again, it's very much simple. You just need to know okay, किस तरह आपने nodal analysis करना है and how you are going to do the cascade. The rest of your life is very much easy. So there's not any big science involved in it. But make sure do these things. They are easy, but they need practice and they need understanding. I'm just trying to RS. Okay. So, and that's the count. Okay. So now I will draw, this is M1. I will draw all the capacitance of this one. Okay. So yeah, my point will be out. So let's start with this input side, जिसको हम लोगों ने पहले X node कहा था, and we said this node as Y. So ये आपके पास input side है, तो input side पे capacitance. So I will draw one capacitance and write all the values on it. ठीक है? So this is your input capacitance. So this input capacitance will have which capacitance? अब आपने देखते जाना है. Am I to also do by? Am I doing? Is there any issue? So first to source. So definitely there will be CGS1 again. Say MS1. Another capacitance क्या होगी? This gate to drain one, which we just found the expression that it will be GM1 divided by GM2. So we are going to have CGD1 1 plus GM2 divided by, just make a little bit room here so you all can see. It's going to be CGS1 plus CGD1 times 1 plus GM1 by GM2. ठीक है? So that ये हमारे पास capacitance, input capacitance होगी. इसमें since we have a cascade, we will have at intermediate node Y also capacitances. ठीक है? It's not only the output, we have intermediate. So हमारे पास 3 poles आएंगे. So we have 3 poles here in this configuration. So what will be the capacitance here? Here one capacitance, the CGD1, but the opposite scenario will come. CGD1 times 1 plus GM. अब GM2 हो जाएगा. GM2 by GM1 plus what will be the other capacitance? This is the drain and the bulk. So CDB1. Make sure do all of these things. This should be another capacitance. क्या होगी? This is the source and the bulk is connected, shorted together because this bulk is grounded and source is not. So there will be CSB2. What else capacitance? This is the source and this is the gate. Gate is grounded, so there will be one capacitance between source and the gate. It might be equivalent to source. You still have to bring this notion. ठीक है? So these all with the capacitances for capacitance on the drain here at the node Y, and there will be some capacitance at the output. Output पे कौन सी होंगी? Output पे we will have gate to drain of 2. ये CGD2 आ जाएगा. तो CGD2 plus what's the other capacitance? Drain to bulk 2. So CDB2. So now you can see only the main thing was that Miller being applied here. The rest is just easy. So you just need to find that one. Okay? You can directly find the R out at this node and you need to figure it. Same thing, R impedance at this point. So you can figure it out easily. The 3 poles. So you will have one pole at X, omega PX, one pole at Y, and one pole at out. आपके पास 3 poles आ जाएंगे. तीनों को you can write it. If you want, I can also write that expression for you, that here this for this node you will multiply this with RS 1 over this one times RS. तो इसको मैं CX कह देता हूँ. ठीक है? Y के लिए क्या हो जाएगा? If we see this junction at this node, so we'll see from this node, so we are going to see 1 over GM2 in parallel with RO1. So ultimately we are left with 1 over GM2 because RO is infinite. So it's going to be 1 over GM2. So it's going to be GM2 divided by, I will say CY this thing. So yeah, आपका expression इसका हो जाएगा. And for output, we already have an RL and we took RO as infinite. Since RO is infinite, so our output will be simply, node will be 1 over RL. And this only because we are considering small RL is infinite. Otherwise, that expression of the cascade will come. So in this case, you can find the frequency response. Once you have those values, you can correspondingly draw the Bode plot, okay, where the first pole is, and each one will have. So first of all, yeah, here I have 2 dB per decade, down I have, let's say, right, minus 40 dB, and then onwards you have when mega P3 will come, you can have minus 60 dB per decade. So something similar you have to do in the homework too. So make sure to get used to these things. They are for, so they are very much helpful. So now what we can do, the something similar, the frequency response we can apply to the differential pair. Everything remains the same. You just need to consider the same half circuit. If it is a differential pair, symmetric pair, you can do the same cut thing on the half virtual ground may the frequency normally find, and you can just find the frequency response of a differential pair. So there's nothing different. Pair. So there are a couple of examples in your book which I would like to do for you. So what I would prefer to do, I will close this session now, and I will do a couple of examples and identify some problems which are variant also from, and like 5 to 7 overall examples plus problems related to in journal about the frequency response. And I will try to upload like before Wednesday or by Wednesday, since you have a mid on Saturday, and these topics are not that they will mainly in the exam, and that will be helping you to solve your the homework. So what I will do, I will try to upload before the Wednesday, rather by tomorrow I will upload some questions, and then you can go through them and make sure to like not only just see, because the problems need to be done by hand. Unless you do by your hand, you are not going to get any benefit. So make sure do by your hand, come to the office hours, ask question. If you have any, we can have any session, special session just for the questions. But please, for that, you need to come out. Okay, these are the queries and this thing you want. Okay, so then we can have some separate session. So I will upload these the content till this point, and we'll have some extra questions, examples basically, and one or two I also want to see, which will cover a little bit broad aspect. But I would highly recommend also before seeing the next one, if you can, I would really like to do example. Yeah, example that's basically somehow related to your homework to example 11.29. That needs a bit time, and I want you to have the digest today's material, because again the today material is building on the top of the previous material. So you should be clarified with some concepts that okay, when you want to do a frequency response and amplifier, the frequency response of an amplifier can be divided into three things basically: the low frequency response, the mid band gain, and the high frequency response. And what you need to do in the low frequency response, you need to identify the capacitance which are going to affect the low frequency. Then, and you have to ignore any other thing. You have to ignore the transient transistor capacitance. And then you have to find the mid-band gain. You have to ignore both the low frequency capacitance and the transistor capacitance, which you used to find previously when we were finding the DC gain. And once you are done with that, then you need to move toward the high frequency response, and then you are going to bring the transistor capacitance, or we normally call the parasitics, you have to bring, and you have to write that. And once you have done that, then you can just write the expression, then you can easily draw the plot. So just make sure you understand these things, and you have applied in a couple of examples, and you are like a common source, common gate, and a source follower. And then we can do one example of 11.29, which is basically a combination of two stages. So like similarly, when I was saying 11.24, so I want to combine them together, that there's a combination of two stages, how the capacitance basically affect two-stage operation whenever we have first stage, for example, and then we have a capacitance in the middle, and then we have the second stage. So how the impact is going to be? Is it a low frequency capacitance? Is it a high frequency capacitance? That we want to see, and what we will do with this capacitance. Basically, we need to separate the impedance at this point, or whatever we want to do. So that's basically I want to do in a next lecture, or one lecture, which is going to be some sort of problem solving questions. Okay. So I will upload the current material, but make sure to go through this thing. And also I noticed that there was like last 5-6 minutes got muted in the previous lecture, lecture 14. So I will also record that session of 5-6 minutes and upload that one. There at the end, I was just solving that part. So there was nothing, but still I will upload. I will record that part again and I will upload. Right. Thank you very much for your attention.